Good to go. Yes. Okay. Good evening, everyone, in person and online. And those online might be used to the usual little slight technical hitch, but we're not a hitch. We're up and running. And welcome to everyone on this Friday evening. First things first, I'm going to start with a very short formalities of our AGM for the year. Doesn't involve too much. We have no new committee members to announce, but we very much welcome anyone's interest. If anyone is interested in further working with us and helping us, then please do let us know. The other announcement is that Richard Taberny, who has been our secretary since 2006, this is his last season there. So we genuinely, well, thank you again next month, but many, many thanks for all of your long help with the Scottish Centre. Whilst I've got you all, if there's any feedback in person or any comments anyone wishes to make around the running of the Scottish Centre or our events, then very welcome to hear them in person just now or afterwards. Email to myself. Does anyone have any comments online or in person? Okay, that's fine. So I bring up my information. So without further ado, we'll begin our talk this evening. So we've got two speakers tonight. And our first speaker is Dr. Katrina Padelman, and she is the Chancellor's Fellow in Energy at the University of Edinburgh, with over 25 years researching the secure and sustainable utilisation of the subsurface for low-carbon energy applications, including hydrogen energy and CO2 storage. Katrina is responsible for a number of UKRI, EU and industry-funded projects investigating underground hydrogen storage technologies. And our second speaker, David Stevenson, is Chair in Atmospheric Chemistry Modelling at the University of Edinburgh. He initially worked at the Met Office, building and applying some of the first global coupled climate chemistry models before moving to the university about 25 years ago. He's been a contributing author to several IPCC reports in the areas of tropospheric ozone, radiative forcing, and changes in atmospheric oxidants and methane. So our talk tonight is titled The Future Hydrogen Economy and Climate, and looking at the benefits and potential problems. So the short abstract is, to meet the global commitments for net zero carbon emissions, our energy mix must transition away from fossil fuels. Hydrogen is gaining increasing recognition as a low carbon energy option to support this energy transition, and is considered a low carbon substitute for fossil fuels to decarbonize domestic and industrial heat, power generation, and heavy duty transport. It can also promote increased renewable energy uptake by acting as an energy store to balance supply and demand. However, hydrogen is an indirect greenhouse gas, as it leads to increases in methane and ozone as it is oxidized in the atmosphere. So this talk will cover the role of hydrogen in supporting our net zero ambitions and what we need to do to ensure that the net benefits of hydrogen for climate are maximized. So without further ado, I'll hand over to our first speaker tonight.
Share screen. That's it. You want to check everyone online can see that, or we're good? They can. Perfect. Excellent. Oh, well, thank you very much all for inviting me to come and talk to you about the future hydrogen economy and the climate, and the benefits and potential problems that it will bring. It's going to be a double act between David and myself. So I shall cover what's the fuss about hydrogen. We hear it a lot. So I'll be talking about the role that hydrogen can play in our future energy system and how it can support our ambitions towards. Oh, yes, certainly. Right. Sorry. Oh, golly, I'm doing all sorts of things. Right. Oh, sorry, you can just do it there. Oh, there you go.
Do that.
And the other one.
And can I minimize that?
We good? Brilliant, excellent. So David and I are going to do a double act. I'm going to cover a little bit about the hydrogen economy and why we need it and what it can do for us. And then David will talk about the atmospheric chemistry modeling that he and his team are doing here at Edinburgh. So we all know the problem. Yeah, this is nothing new to you all. We need to do something about the increasing greenhouse gases in the atmosphere. And I always think it's really important to kind of remind ourselves of where they're coming from. So the graph on the screen that you can see shows you the UK emissions per sector in 2020. And what you can see here is that 78% of those emissions are coming from the burning or use of fossil fuels. So this is a major problem. We've got to do something about this. So that's whether it's in transport, that's whether it's in our energy supply, it's whether it's in our business heat and industrial processes, or our residential heat. Okay, so this is a really, really big challenge that we need to tackle to try and solve the greenhouse gas emissions and reduce those atmospheric values of greenhouse gas. And we are making progress towards this. Yeah, we are taking steps to do this. We have legally binding targets. More and more countries are signing up to net zero targets. We have the Paris Agreement. So there is a global effort to try and reduce these greenhouse emissions and recognize the importance of kind of that transition towards away from fossil fuels and towards a renewable energy-based system. So this is, I think it's really the graph of shame, in all honesty. So this graph here shows you amount of millions of tons of CO2 over time projected into the future with the decarbonisation paths that we're following. And this is for the different sectors. So this is for transport, this is for industry, this is for homes, so heat, services, refineries, and of course, electricity. So the first one you can see that's most dramatic, of course, is the red line, which is electricity. Yeah. So, I mean, in reality, we've done a very good job of decarb or reducing the amount of CO2 from our electricity supply. And that wasn't easy to do because we switched our coal-fired power stations to gas. Yeah, that's what we did. And suddenly, so that's why you get such a dramatic shift. You close the coal and you change everything to gas. That was an easy win. Yeah, so everyone's sitting there going, oh, aren't we great? We're meeting our targets, aren't we doing well? But it's really the hard stuff that's going to be challenging. And I think net zero, that net zero target means we have to do the hard stuff. You know, it really upped the ante in terms of what we were doing. So if you look at all the other sectors, the progress is very limited. And don't forget, this is still a projection. It's not going to happen, not the way we're going at the moment. So yes, we're making great progress with decarbonising our electricity. You know, we've got better energy efficiencies, we've changed our light bulbs, we've done all that. We're installing some heat pumps in modern houses that are insulated well enough. We've switched from coal to gas and we've got way more renewable energy, which is great. But as I say, we've made limited progress reducing the other hard to electrify sectors. And these are something that we've got to do. So we need more solutions for these hard to electrify areas, and we need more solutions to support renewable energy because that is the clean way of providing energy for the future. And I just think it's always worthwhile. I mean, some of you might have these trackers that look at your electricity use and how much of it's coming from renewable energy, and you feel really happy because you're seeing, oh, brilliant, look, 100% of my electricity is coming from renewable energy. But 80% of the total UK energy demand still comes from fossil fuels. Yeah, that is the reality. And it's only dropped 10%, it's only dropped 10% in the last 10 years. So, and most of that was the fuel switching. So we really need to, do better, shall we say. I won't rant too much, I promise. And I think this graph here really shows the challenge ahead of us, okay? So this is a fantastic graph by Grant Wilson at Birmingham University, who's incredible at pulling the data out of the kind of energy systems. And what you can see here is this line here, that's our renewable electricity, okay? The red line, that's our total electricity, yep. The blue line, which is waving its way across there, no surprise, that's our heat, that's our gas for heating. And then the black line is our transport. Okay, so these are the kind of patterns that we've got to do every year, year on, year out. We see this incredible cyclicity to our energy demand for heat. It's not a surprise. But I think this graph is really important for two things. So first of all is the message that we need to drop these curves in total. We want to bring them down. So we want to bring them down by changing our habits. It's very difficult to do, telling the kids to switch the lights off, blah, 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 blah. We need to do all of this. We need to improve our energy efficiencies, perhaps reduce our transport, share transport, get on our bikes, all the other things that, we know we need to do, but are actually quite challenging. And then if we're really going to move towards this renewable system, we've got two challenges ahead of us. The first one is to fill the gap in electricity. So let's get more of our electricity off, because this gap here is provided by fossil fuels. Yeah, that's the bottom line. So we really need to up our renewables. And somehow we are going to have to get our renewable electricity to provide that massive, massive increase in demand over the winter, where we can literally go from, a total energy demand of kind of 1,000 gigawatts per day all the way up to 3 in a matter of weeks. Yeah, and that runs the whole winter. So this is a real challenge, because how on earth can we make sure that the renewable electricity is going to deliver that level of reliability? It never blows when you need it. So there's this mismatch between supply and demand. And that mismatch in renewable energy between your supply and the demand is really summarized by this thing called curtailment. I don't know if many of you have come across that. You pay £10 a year for the privilege of having your energy curtailed. But basically what curtailment means is that it was necessary to get electricity up and running, renewable electricity. It was a sort of contract for difference, because they knew that obviously the wind is unreliable. We needed to get wind power built out. So it was an agreement that meant that the renewable energy suppliers would get paid even when the wind wasn't blowing, but the demand was there. And the big problem is the electricity grid is just simply not beefy enough to deal with this. So even if people wanted the demand, even if people wanted that electricity, the grid wasn't strong enough. So they get paid when they're generating electricity, but nobody needs it because we're all asleep. And they get paid when they're generating electricity, but nobody can do it. So all of that has to switch off. It's completely wasted. So that's cost just over £1 billion already in that balancing mechanism. So that's 16 terawatt hours of energy that have just been wasted. Nothing we can do with it if we don't store it. If we don't, and batteries just simply are not going to store terawatt hours of energy. And of course, this is getting worse and worse as we build out more and more renewable energy at a rate that's faster than we're building up the grid. And you can see on the graph here that Scotland onshore is heavily curtailed, yeah, because the demand centres are down here, yeah, and the electricity grid just doesn't go that way. So it's really important that we think about how we can make sure all of this wasted energy is not gone to waste. So one of the ways we can do that is through energy storage, using that renewable electricity, generate hydrogen through electrolysis, store it in geological formations, hence the fact that it's an area I'm working in, and really just try and make use of that wasted energy so that it doesn't, it costs you all money and it's only going to get worse. So I've mentioned the fact that hydrogen is really, really good for supporting the renewable energy, providing that really massive energy storage, not just to reduce curtailment, but to supply the energy that we need in the winter. But it also has a kind of secondary role in that because it can be burnt and used in the same way as a fossil fuel, it's very good for supporting those areas which are hard to decarbonize. So this is where it gets a little bit controversial, shall we say. Some people think it might be useful for heat. Who knows? We should all be electrifying, but that's not easy in our old houses, because we're not allowed to insulate them. And anyone who lives in Edinburgh, you're not even allowed to put double glazing in if it's not fancy. So these are quite challenging things to tackle. So it can be combined with captured CO2 for industrial feedstock. They just need a C and an H for their chemistry. So maybe hydrogen can be used for that. It certainly can help with long distance transport, not for small distances, but certainly for long haul, heavy transport. A fuel cell vehicle doesn't require a sort of recharge stop. It just can get filled in the same way. So there's a number of areas where hydrogen can do that. So these roles for hydrogen that can really tackle these challenging areas are why governments around the world are so interested in hydrogen. So this map here shows you all of the documents, all of the policies that have come out of the UK government and the Scottish government and the devolved governments since 2020. Yeah, so this is a really new field. Hydrogen was just kind of, I mean, it's had things in the past, but in the recent times, it was briefly mentioned in the Committee for Climate Change report about how it could support decarbonisation. And before that, we'd started kind of researching in it. So the work I did started a little bit before that because I quite like hydrogen, so it's really neat. But suddenly, in the last, 3-4 years, we've had a wealth of reports culminating in the UK hydrogen strategy, and there's one for Scotland as well. So hydrogen's gone from zero to kind of hero, really, if you feel like that it is, or certainly a lot of hope is being put in it. You can imagine in Scotland, with our incredible renewable resources, the Scottish government is pinning a lot of hope on hydrogen because we can export it to countries that want it for decarbonisation. So, we've got the facilities. As you could see on that curtailment map, we make a lot of excess renewable energy. So, a lot of the governments you can see. And then, of course, we had the gas crisis when in the Ukraine invasion. Suddenly, the gas prices went really, really high. And everybody realized how vulnerable their energy supply was. So that made a big difference in terms of driving ambitions for hydrogen, because it's a kind of sustainable, it's local, it's energy storage. So it gives you that security. It stops you relying perhaps on imported gas, and you can make it basically homegrown energy. So that really is a very, it's a quick timescale. So we've gone from nothing to hydrogen cars, hydrogen buses, hydrogen transport networks. Everything is in place in a very, very short period of time. And this graph here shows you just how much the UK government and the Scottish government really want hydrogen and see hydrogen as part of their future energy system. So what we can see here is that when you're doing your kind of energy system modeling for net zero, none of them reach net zero without hydrogen. Without hydrogen to support renewable energy, maybe without hydrogen to decarbonize some of these industrial processes and transport. They just don't reach zero or the target by 2050 if they don't have hydrogen. And, look, we've got two different kind of scenarios, future modeling scenarios. We've got the UK government net zero strategy, and they think that even if we were to electrify everything through renewable energy, they are still going to need 240 terawatt hours of hydrogen by 2050. This is a lot of hydrogen, yeah? And then in the National Grid future energy scenarios, which is another kind of quite well-respected energy kind of modeling system, again, in their full electrification, they're still looking at 13 terawatt hours of hydrogen per year required. And the bottom line is that by 2050, most of the UK's, they anticipate, that hydrogen could be delivering between 20 and 35% of our total energy demand in that. So to put that in context, that's basically the flip opposite of what we've got at the moment. So at the moment, we have 80% fossil fuels, 20% electricity. By 2050, we could be looking at 70 to 80% renewable electricity and 20 to 30% hydrogen. So hydrogen could become as widespread as electricity is today in terms of its total contribution to our energy. Don't know how my time's doing, but I'll keep going until someone stops me. And then I just wanted to kind of go through the different ways we can make hydrogen. I don't know how many of you are familiar with that, but sometimes it's quite useful to know. But at the moment, most of our hydrogen is produced from fossil fuels with unabated emissions. So at the moment, you basically reform methane, split the C and the H, produce an awful lot of CO2, and that generates your hydrogen, and that's used in ammonia or refining or a whole host of different areas for fertilizer and other things like that. And it's responsible for a massive amount of emissions, 900 million tons of CO2 in 22 alone. So it's this grey hydrogen industry is not a clean industry at all. And it's just growing. In the UK, so for anyone who's thinking, do we make hydrogen ourselves here? Yes, we do. we make around about 23 terawatt hours per year across 31 sites. So those tend to be refineries. So say, for example, Grangemouth, they'll do their steam reformation for use on site for hydrogen. And this is really the way it's going. It's the cheapest kind of hydrogen, but its emissions are really unforgivable. So we have to move away from that. So there's two ways we can move away from that. The first one is to capture the emissions at source. So when you're generating your hydrogen, capture those emissions, capture the CO2, and then store them in the subsurface securely, which is very much doable. The CCS, the carbon capture and storage technology, is very well advanced. And there's no reason why we can't do that. And actually, there's 3 projects underway in the UK that are starting to go through their initial studies to do exactly that. So in Scotland, we've got the Acorn project at St Fergus, and then in England, they've got a project in Teesside, and the HyNet project as well, both in the north of England, on the east and the west of the country. So there's ambitions to do that. At the moment, we don't do any carbon capture and storage with our grey hydrogen, but certainly the ambition and the funding has been put in place to make these 3 projects happen and start that. And then, of course, there's the lovely green one, which is green hydrogen, and that's simply splitting an H and an O. So we just, I forgot to bring my little hydrogen generator. Oh, I have a little kit. I'm really annoyed. We can basically, you just send an electricity across a membrane into water, and you can get your hydrogen and your oxygen. And this is definitely an area for significant growth. Green hydrogen is more expensive, but that's simply because the electrolyzer technology hasn't really been beefed up to the amount it needs. It will come, the costs will come down, and it should be cost competitive with the other technologies within the next couple of years, by 2035 is anticipated. And we do produce green hydrogen in the UK. We produce 2 metric tons a day of green hydrogen. Yeah, not so much, but it's better than none. So that's 26 gigawatt hours in terms of energy from 14 sites. So if you want to buy hydrogen, it's very challenging, but we are making it. However, there's an enormous government drive and funding being put in place, the hydrogen electrolytic round. So there's now 17 new projects that are going through some funding support mechanism to get these projects happening. So again, this is only in 4 years that we've had all this progression. And then one of my kind of favorites is the natural hydrogen, or gold hydrogen, as they call it. So from a geological point of view, this is naturally occurring hydrogen. So there are many geological processes in the subsurface that can produce hydrogen. And so people are suddenly out exploring for hydrogen. It's like a new gold rush, because there's a lot in Australia. There's a village in Mali. They've been producing hydrogen from a well for about 9 years. It runs a fuel cell in the village. So they don't know where it comes from. They don't know how to manage it, but they've been getting free energy for the last 8 years, and they're delighted about it. And there's a company recently who estimate that there's 1 million tons of hydrogen under the Pyrenees in Spain. So they're now touting for business to try and see whether someone will invest in that. I'm not sure they have yet, but they're looking at sort of under a kilogram, dollar per kilogram for that. So these are kind of quite exciting, especially for geologists. We're like, oh, new places to look. So it's really good. And then I also just wanted to show you that we, in terms of the ambitions to move hydrogen, you obviously need a transport network. We can use tanks, but they're not going to be big enough, or trucks. They're not going to be big enough for the ambitions. So what we have is the European backbone. So that's a huge, big European effort to map out how we can set up a whole European-wide hydrogen distribution network. So this plays very much into David and Hannah's work, because lots of pipes, lots of joins. So the ambition is that. So the idea being that we'll either repurpose where we can, because it's cheaper, and then we'll build new where we need to. And certainly, this is again starting to happen. They're mapping these projects. They're testing the out of use pipelines that could be repurposed. So there's testing underway to get that happening, to connect the demand centers, the storage and the production. So again, from nothing to zero. And then into my area, which is the storage, which again is another area. So we've got the production side of things where we can be doing fugitive emissions. We've got the transport side where we can be releasing fugitive emissions. And then we've got storing hydrogen. So when we look at kind of the same scenarios we saw when we were looking at the kind of energy demand that is out there, that goes with storage. Yeah, so if we look at the UK National Grid futures scenarios, they're looking at 56 terawatt hours of hydrogen to be stored in the subsurface by 2050. Yeah, that is a huge amount of hydrogen. Same in Europe. So in Europe, they're looking at 70 terawatt hours a year by 2030. They're really holding hopes for hydrogen, particularly with what's going on at the moment. And even in the US, they've got an ambition to decarbonize their electricity grid. So they're still looking at hydrogen for that. So 100 terawatt hours of storage a year. So, you know, the geologists are going to be busy. And there's a whole host of geological storage technologies. We can store them in lined rock caverns. So we excavate the subsurface from hard rocks, coat it in cement or line it with cement and steel, and we can store hydrogen there at high pressure. We've got salt caverns, so we've got a lot of salt deposits. We basically dissolve out caverns in the salt. It's nice and tight. It keeps the hydrogen in place. And we can use our depleted gas fields. And we've got infrastructure, we've got experience. So the depleted gas fields are a very attractive option for that North Sea transition as well. And the reason why we need the geology is that hydrogen, while it has the highest energy density of any fuel, you know, its small mass means that by volume, it's just really hard to get the same energy density as you get when you're comparing it with fossil fuels. There's no getting away from that. You know, this graph here shows you kind of the energy density of hydrogen per depth. So looking at the geothermal, the temperatures and pressures increase with depth in the subsurface. And you can see at the surface, the density of hydrogen is 0.2 kilograms per meters cubed. But if you go down and, you know, maybe 1,000 or 1,500 meters, suddenly you're getting 20 kilograms meters per cube, just because if you've got that higher pressure and temperature. So you can see why the geological storage has the scale, it's big enough, the subsurface is pretty big, and it has that advantage of being able to store things at high temperature and pressure, which gives you that extra energy density. And I mentioned lots of different technologies, so nice pretty pictures. We can store them in coils of tubing. There's already 4,500 kilometers of hydrogen pipeline in the world anyway. We know this is something we can do. We can handle this very safely. We know the right materials. We know how to deal with it safely. So that's a really good option for some smaller scale projects that, you know, can be geographically located anywhere. We've got silos, which are basically kind of vertical tubes that can be held at quite high pressure. Again, you can put lots of those in a field. So one field can say, you know, hold 300. Well, one tube can hold 300 kilograms of hydrogen, so they can hold quite a lot. We can do lined shafts or lined mine workings, and our lined rock caverns, which I mentioned, are excavated out of this nice strong rocks. And then we've got our salt caverns and our porous rock reservoirs. So these are really the areas we can store that. And again, just to kind of highlight how quickly things are happening for storage, this is a map of all the planned hydrogen storage projects that have come from nothing to potentially being operational in quite a short period of time. And that's across Europe. You know, 29 projects, 3 of them in depleted gas fields, 3 in lined rock caverns, and then the majority in salt caverns. Salt caverns are the easiest one to do. We have stored hydrogen in salt caverns for 50 years in Teesside for the chemical industry. So this is something we know how to do. So that's why you can see that countries with salt deposits are laughing. They're like, oh, great, we can store our hydrogen, no trouble at all. So it's all happening. And now I shall finish as I hand over to David, just to kind of remind you about that future hydrogen economy. So, you know, I think it is an essential future energy carrier. You know, it can be handled in the way that natural gas can be used. It really can tackle these challenging areas. You know, it can provide that energy storage that we're going to need without question for our renewable energy. We have to move to a renewable energy system. So we have to do everything we can to support that. It is very energy dense, which is great. It burns cleanly. You know, you just get a little bit of water vapor and NOx perhaps, but David will talk about that in more detail. It can be sustainably and homegrown produced, which I think is really interesting, from electrolysis and excess renewable energy. And it is versatile and cheap to transport in bulk. So it uses in a similar way to natural gas. So we feel comfortable with it. But it's not the main, you know, it has a few problems, yeah? It's not the perfect solution. It costs money to make, yeah? There's no getting away from that. You know, until we find naturally occurring hydrogen, it costs a lot of money to make. But sometimes we have to just, it's not always the most efficient way. You know, we've got to tackle these challenging bits, and you can't do that without maybe that additional cost. So sometimes the benefit of that extra cost outweighs the cost, as it were. So it does need large-scale storage, which is good news for the geologists. Public perception is going to be interesting. It's come very quickly, so I think it hasn't kind of reached people in the way that maybe it has done. It will do soon when these projects start happening. So, all of these projects are in their design stage at the moment. But at some point, someone's going to either dig a hole or develop an electrolyzer site near where people live. So it's going to be really interesting to see how they feel about that. There's a lot of misconceptions about the safety to do with hydrogen, and people are absolutely right to be worried about that. There's many kind of features of hydrogen that actually make it safer. But people think of it very negatively. So the public perception is going to be really important. And of course, it's an indirect greenhouse gas. So we can't just, leak it and use it with gay abandon. So over to David.
I can try. You know how to do that? Does anybody know how to move the more? Is it more? Hide floating. Okay. Okay, so on to part 2 of the talk. So this has the same title. I just want to acknowledge a few different people. So Hannah, who's in the audience, and Alex are both working with me on modeling the atmospheric chemistry associated with hydrogen. And I'd like to acknowledge Dick Derwent as well, who introduced me to the atmospheric chemistry about 25 years ago, and has always been hassling me with more work to do about hydrogen. He's been working on it all of that time, really, while lots of us moved on to other things, but it's always been an interest of his. And Maria Sand and others on the hydrogen project, so they're providing some of the funding for this. So they're based in Oslo at Cicero. And I'd just like to acknowledge both funding from them through the Research Council of Norway, and also some recent funding from UKRI through the Hector project. And we've also got some European money, which I'm quite excited about, that hasn't arrived yet, but is happening over the next few months. So that's quite exciting as well. And also some of the results I'm going to show you using Archer 2, which is the UK's supercomputing. So thanks to all of those people. So I guess I'm interested in what happens to hydrogen when it gets into the atmosphere. So I think there are perhaps 2 common misconceptions about atmospheric hydrogen that I've just written down here. Maybe these are not misconceptions that you've got, but just in case they are, I'd like to get these out of the way. So hydrogen is a light molecule. It drifts up to the top of the atmosphere and into outer space. This is wrong. It is a light molecule, but like all gases below about 100 kilometers, it's well mixed in the atmosphere. So gases don't segregate out just because they are lighter. Doesn't matter about their molecular masses until you get to very low densities and high up in the atmosphere. I think the other misconception maybe is this, that hydrogen oxidizes to water. So it's a clean fuel. It has no environmental impact. So again, this isn't quite right. It does oxidize to water. I'm not going to dispute that. But that doesn't necessarily mean it has no impact. So hydrogen is not a direct greenhouse gas either. So it doesn't interact with terrestrial radiation or indeed solar radiation. But it is an indirect greenhouse gas. And this is because its atmospheric chemistry means that it reacts with a species in the atmosphere called the hydroxyl radical. And that is the main sink for methane in the atmosphere. So we perturb the cycle or the life cycle of methane and ozone in the atmosphere. And these are both greenhouse gases. And actually, some of the hydrogen is long lived enough to get into the stratosphere, and the methane the extra methane that it produces as well, and that water in the stratosphere we are worried about as a greenhouse gas. The stratosphere is very dry, so any perturbations there to the water cycle are actually a big deal. Creating water down at ground level, we don't really care about, because the natural water cycle in the troposphere is so big that it's not an issue. So going back to what the hydrogen economy looks like, I just want to think about potential environmental impacts from building all of this infrastructure and using hydrogen as a fuel. So we talked a little bit already about grey hydrogen. So the hydrogen production method is important. I think we've highlighted this already, but just to put this all together. So if you produce your hydrogen through this grey route, as we are at the moment, it's not good news. You will produce some CO2, and you're using methane as the feedstock for quite a lot of this as well. So you will leak some methane. So you will be producing some of these greenhouse gases. And even if we get a blue hydrogen, okay, we should get rid of the CO2 because we're storing it underground. But the methane is probably still an issue unless we're pretty careful about how much methane that we leak. And I suppose we've seen the news in the last few days actually about Kazakhstan leaking huge amounts of methane. So I think we have to be a little bit worried about how much methane is still being leaked into the atmosphere if we go down the blue hydrogen route as well. So green hydrogen really is the answer. So we need to get that from our renewable electricity, as has already been described, electrolyze it and produce hydrogen. So those are the sort of some of the hazards to do with the hydrogen production side of things. But once we've got hydrogen going through our pipelines and being stored, I mean, I'm sure it can be stored very safely, but there will always be some leakage of hydrogen to the atmosphere. It has to be transported around through pipelines or in ships or in trucks or whatever. I think people from the hydrogen industry tend to point out that hydrogen is going to be very valuable and they won't leak very much of it. And I'm sure this is partly true as well, but we don't really know how much hydrogen is going to leak into the atmosphere. So this is a bit of an unknown. But any of that hydrogen that does leak into the atmosphere, as I've already said, is going to potentially perturb methane, ozone, and stratospheric water. So this is where its indirect greenhouse effect comes in, really. There are a couple of other aspects that I'm not going to really touch on. I'm sure I will be asked about some of these, but one of the ways that we might transport hydrogen around the world is by converting it to ammonia, because ammonia is a bit easier to liquefy and transport in order, for example, to get long distances. So there are plans, for example, to produce lots of hydrogen in Australia and then have a market maybe in Japan or other parts of the world. So that needs to be transported by a boat, and it could be in theory transported as hydrogen itself, but in many ways it's easier to convert it to ammonia. And ammonia has various environmental impacts. So again, we don't want to be leaking lots of ammonia into the atmosphere. We already produce enough from agriculture. We know that it's kind of bad news. And the other thing, just to point out, again, I'm not really going to say anything about this, but the end use of the hydrogen is also potentially important. So if we use it in a fuel cell, that is the cleanest way of extracting the energy from the hydrogen. And that should be good. But if we are putting it into our gas boilers and just burning it rather than burning methane, that combustion will also produce NOx. So we have to be careful about how much NOx we produce, because that can also have some impacts on the atmosphere. Okay. So with all of those different impacts, I want to ask this question about net zero, because I get confused about net zero, to be honest, and it gets used an awful lot. So I want to sort of pose the question of what does net zero actually mean? Again, maybe you're way ahead of me, but I don't really want you to read this, but this is an IPCC, Intergovernmental Panel on Climate Change definition. which is kind of long and wordy, but it points out really when you have multiple gases, multiple greenhouse gases involved, you basically need an exchange mechanism between those different gases in order to quantify the overall impact. And so you need an ability to compare the climate impacts of different gases if you're emitting different gases. And this is really how we calculate CO2 equivalent emissions. So we need basically a conversion factor for hydrogen. If we're going to emit some hydrogen, what is that equivalent to in terms of CO2? And the way we do this traditionally is to use what's called a global warming potential, a GWP, and we need to specify the time horizon. I'm not really going to go into the details of GWPs, but essentially they are this exchange mechanism between hydrogen emission, and 1 kilogram of hydrogen is equivalent to how many kilograms of CO2. Now, there is much debate about whether the GWP 100 metric is the one to use, but it is essentially the metric that's written into lots of the global agreements about climate change. So there's been efforts basically to produce a GWP number for hydrogen, and that's what I'm going to talk through in a little bit more detail. Of course, we also need to quantify how much hydrogen we're going to emit. This is very unknown, very uncertain. What fraction of the hydrogen that is in the hydrogen economy is going to be leaked into the atmosphere? But that's quite an important number. And really, to get to the bottom of, or to try and calculate a GWP for hydrogen, we need to know the life cycle or budget in the atmosphere of hydrogen. So I'm going to give you a little bit of background about just global measurements, what we know about hydrogen in the atmosphere, because we haven't really studied it in a lot of detail. It hasn't been one of the gases that we've been too worried about in many ways. So there's some very recent data that's pretty useful. So this first graph here is basically ice measurements. It's actually firn air rather than ice core. So firn air is the unconsolidated snow where you can extract air from that, and it actually gives you a record of the recent past rather than ice cores going back hundreds of thousands or thousands of years. And this is a study that's basically extracted that air from firn ice and worked out what has happened to the hydrogen concentrations in the atmosphere over the last 100 years or so. And we can see that hydrogen has increased by about 67%, from about 330 parts per million up to about 550 parts per million over parts per billion, sorry, over the last 100 years. So it's been going up, and this also is sort of confirmed by direct measurements from the atmosphere as well. So which is just the little last section of this graph that I've tagged on. So these are the direct measurements from a network of NOAA sites. So I'm going to show you a little bit more information on the next slide. But essentially hydrogen is increasing in the atmosphere, and this is presumably due to anthropogenic activities. We've been sort of manufacturing it for the last 100 years, I guess, mainly for fertilizer use. So just a bit more detail about those measurements of hydrogen from the NOAA network. So this is the National Oceanographic and Atmospheric Administration in the US. They run a global network of sites measuring lots of trace gases, including hydrogen. And they got some really nice data. So I stole this. This is an animation, actually. So let this hypnotize you for a few minutes. So these are measurements from basically this global network. And we're basically looking from the South Pole to the North Pole. And there's about 60 sites or so across the world. And this is running from, I think it started in the late 90s up to about 2016, this animation. So you can sort of see, first of all, there's two things really I want to point out. It's basically that hydrogen is higher in the southern hemisphere than the northern hemisphere. Not by much, but there is more of it in the southern hemisphere. And this is kind of interesting I don't think any of the other trace gases that are influenced by anthropogenic activities have a higher concentration in the hemisphere that is sort of less perturbed. The other thing, let me try and start that again. Oh, now I've blown it. The other thing to point out is there's a seasonal cycle. So you can't necessarily pick this up, but you can see this is going up and down. These are monthly values. And you can see that the seasonal cycle, or the changes in the concentration in the northern hemisphere, are bigger than in the southern hemisphere. And this is really because the biggest sink for hydrogen, both of these factors are really all to do with the fact that hydrogen is partly controlled by its soil sink. It's taken up by microbes in soil. And there is more land in the northern hemisphere. So that basically means that the sink for hydrogen is bigger in the northern hemisphere. That's why it's got lower concentrations in the northern hemisphere compared to the southern hemisphere. And it's also why the seasonal cycle is bigger. So this is useful information for us to test our models of hydrogen in the atmosphere to see if we're getting the right answers. So just an overview of the overall hydrogen budget in the atmosphere. This is our sort of, we don't know lots of this, but there are various sources over on this side of the slide. As we've already talked about, there's some geological sources, very unknown whether they are big or not. So there's a really big uncertainty on the geological sources. And then there are some sources from fossil fuels that we know about quite well. And then other sources like biomass burning and nitrogen fixation as well produce some hydrogen into the atmosphere. But actually the biggest source is produced in the atmosphere from photooxidation of other gases, really hydrocarbons breaking down, releasing hydrogen to the atmosphere. So that's actually the biggest source, we think. So that's an atmospheric chemistry process. And then on the other side of the budget is how is hydrogen removed from the atmosphere? It reacts with OH, as I've already said, and this is the link to an influence on methane and also ozone. But also about maybe 3/4 of it is taken up by soils. And it's actually the uncertainty in the soil sink. Okay, so maybe I should take a step back and we can, by knowing how much hydrogen there is in the atmosphere, so we know there's about 530 ppb. There's a typo there. That's very bad. Sorry, that should be a ppb, not ppt, for hydrogen. We know how much there is in the atmosphere, and we have an estimate of how fast it's being removed. So we can actually work out the turnover time of hydrogen in the atmosphere, and it's of the order of 2 years. But again, there's quite a big uncertainty on this. And its lifetime is really important for calculating the GWP. We want to know how long it persists, and we need to know that lifetime in order to calculate the time integral of the radiative forcing, which is what the GWP is based on. So the uncertainty in this soil sink leads to quite a big uncertainty in the overall climate impact of hydrogen emissions. So we want to try and understand, get a better number for this GWP. So we've been doing some Earth system modeling of hydrogen in the atmosphere using the UK's global atmospheric chemistry model, UKCA. This has been jointly developed by the Met Office and the National Centre for Atmospheric Sciences. And it's the atmospheric composition component of the UK Earth System model, UK ESM1. And that's the model that contributes results to the IPCC and via the CMIP6 process. And I'm going to show you a few results from some atmosphere-only simulations. That just means that the ocean isn't fully interactive in this. We're using sea surface temperatures and sea ice from observations. And it's at a resolution of about 1 to 2 degrees with about 85 vertical levels, going up to 85 kilometers in the atmosphere. And I'm going to show you a present day simulation or results from a present day simulation. And then the great thing about models is we can do these just what if experiments. We can basically add an extra 10% hydrogen and see what it does to these other trace gases. So just to convince you that the model is doing quite a good job, This is one of Hannah's pictures. We've looked at the seasonal cycle of hydrogen at lots of sites, the sites in the NOAA network. And we can compare what the model is producing with what the observations show. And actually, the model is pretty good at producing this seasonal cycle. You might disagree with me, but so each one of these little squiggles, you can't see my pointer. Anyway, each one of these little black and red squiggles is the seasonal cycle. This is a year of data with monthly values, and you can sort of see that the black and the red generally line up quite nicely. If you look very closely, you will realize that the numbers on either side are slightly different. So there is a bit of an offset, but we've done some, or Hannah's done some more runs where we've actually worked out probably what the reason for that is, and actually we can get the bias removed as well. So really that's just to convince you that we can do a reasonable job at simulating hydrogen in the atmosphere, or the seasonal cycle of hydrogen. And we can also diagnose from the model the chemical fluxes, so both the production and the loss. And these are dominated by two reactions. So this is formaldehyde being photolyzed is the main atmospheric source. This is coming through all the hydrocarbons. Most of them end up as formaldehyde, HCHO, and they get photolyzed and produces hydrogen. And then this sink is reacting with OH. That is the dominant sink. There are some other small sinks, but they are really only operating in the stratosphere. Most of this chemistry is going on in the troposphere. So the picture on the right is a vertical profile of these different fluxes, really just to show you that we can see those in quite a lot of detail and see what's going on at different levels in the atmosphere. So really what's going on is we add hydrogen to the atmosphere, it reacts with OH. One route of that is that you're depleting the OH in the atmosphere, and because that's the sink for methane, you're changing the lifetime of methane, making the methane last longer, and so methane builds up more. The other product of this reaction is a peroxy radical, and that ends up producing ozone. So this is where the extra ozone comes from as well. So basically, you get increased ozone and you get less OH. And you also get some water vapor in the stratosphere. So we can quantify those things. So again, these are model results. So this is our change in OH. You can see for a 10% increase in hydrogen in the atmosphere, we get a change in OH of about 0.5%. So that doesn't sound like very much, but that factors into changing the methane lifetime. And by quantifying this, we can work out the overall impact of a change in methane on, a change in hydrogen on methane. And similarly, we get an increase in ozone. It's only a fraction of a percent for our 10% hydrogen, but we just want to know that number. The 10% experiment is not, the magnitude of the experiment isn't important, it's the ratio of these numbers, so that now we can use these numbers to then estimate the overall global warming potential impact of hydrogen. And actually we've done this in several models now, and we get pretty much the same results. So we think it's quite robust. This is a series of different global models. Our model is just one of these, the UKCA model in the middle here. And we can quantify the contribution to the global warming potential from methane, from ozone, and also from the stratospheric water. So that's what the different colors are on here. And we come up with a number of about 12, plus or minus 3, or thereabouts. And this is stuff that we've published in the last year or so. And there's reasonable consistency about this number. Okay, there is quite a large uncertainty. And like I said before, a lot of the uncertainty in this number really comes from not knowing the lifetime of hydrogen in the atmosphere very well. And that's really determined by the soil sink. So there's quite a lot of research going on to try and understand better the soil sink. Are we quantifying it right? What are the dependencies for that? Really, in order to get a better value for this GWP. Now, once we've got a GWP, if we've also got an estimate of leakage rates, from hydrogen. So this is another study that I've had nothing to do with, but this is looking at basically estimated emissions rates for hydrogen through all the different processes within the hydrogen economy to sort of identify where the leaks might occur and where the most leaky processes are. And there is a big range of numbers. So some processes are very good, don't leak very much, but some parts of the hydrogen value chain are very prone to leak. For example, if you liquefy hydrogen and try and transport it in a truck, you may get leakage of up to something like 20% is the sort of highest number on here. But this is again a big area of research to try and work out how much hydrogen we're actually going to leak if we do build this hydrogen economy. How leaky is it going to be? And we need to know that. So I think this is a very technical picture, but this is about the last picture I really want to show you. This is really looking at if we go down a blue hydrogen route, i.e. carbon capture and storage, but still producing it from fossil fuels. We need to be very careful about how much methane that we leak, because if we leak more than about 1% of the methane involved in that process, then it's going to be a very little net benefit for climate. So we have to really, if you're going to go down the blue route, which is not really what we want to do, then you really have to make sure that you're not going to leak any of the methane in the supply chain that's coming up. Now, if we go down the green hydrogen route, this lower graph is kind of telling you that the net or the break-even point is if you leak more than 10% of your hydrogen. So as long as you leak less than 10%, there is a net benefit for climate, and obviously that gets better the less you leak. So really, we need to know. I mean, I think it's looking unlikely based on these leakage sort of statistics or ideas about leakage that we're going to leak as much as 10%. But we do need to keep an eye on this. If we're going to leak a lot of hydrogen, then it's not really worth doing. Okay, so just to summarize, really, the hydrogen climate impact depends on how you make your hydrogen, whether it's gray, blue, green, or other, the leakage rate of hydrogen, and if you're not making it through the green route, then the associated leakage rate of methane is pretty important as well. There may be some climate impacts through the distribution network. Really, this is, again, leakage. But again, if we're going to convert it to ammonia, that might have other climate impacts as well as other environmental impacts. We have a number for the global warming potential for hydrogen, but there is quite a lot of uncertainty associated with this, and it's really all to do with modeling the soil sink. And we need to sort of improve that to constrain our numbers. And I didn't really say much about this, but the end use of the hydrogen is also important, whether you use it in a fuel cell or whether you burn it. And really, that's all about climate, but there are other impacts on air quality and stratospheric ozone that we maybe need to worry about. So there is much we need to check to ensure that hydrogen really is the clean fuel that it's that we think it might be. I think most of these are not insuperable, and we probably should be, you know, it is probably a good idea, but we just need to be careful about lots of these things and make sure we understand what goes on if we leak lots of hydrogen to the atmosphere. I think that's the end. Thank you.
Thank you very much, both, for a wonderful talk. It was a real learning session for me. It's not my topic, so that was really interesting. Thank you very much. I'll open the questions to the floor, initially in person, and then we'll come online. For those online, if you are able to ask a question directly, if you put your hand up, then we can actually you can interact with David and Katrina directly, or you can type your question into the chat. But we'll first see if they've got any questions in the floor initially. David,
well, thanks to both of you for a very interesting presentation. Two aspects to my question. what do you assume is the dry deposition velocity of hydrogen at the ground? And do you assume that there's a mechanism, or do you fix it? What do you have it regulated by? And the second one is the cycle in Antarctica. Is that simply the atmospheric chemistry, or do you assume it's also deposited on snow?
Okay, so I must admit I don't have in my head what the deposition velocity is, but this is what's really controlling this. It's controlled by the soil sink. I don't know, Hannah. Do you know what? No. Okay. I mean, the process that's mediating this is microbes in the soil that are eating the hydrogen, which is another interesting topic in itself, really, and is also relevant for the storage aspect of this, because people were worried about storing stuff in reservoirs and it all getting eaten by microbes. But so the way we simulate this in the model is pretty simplistically. We have deposition velocities over different land surface types in the model. So there are some measurements. So there are, for example, some people at CEH measuring hydrogen deposition. And there are a handful of data sets for different soil types. And so we have those numbers, and we have some dependence on at the moment it is there are more sophisticated schemes where we have like a soil moisture dependence. So people think that the microbes are happiest at a certain soil moisture level, and if it gets too dry, they get stressed, and they don't eat so much hydrogen. And similarly, if it's too wet, you block up the soil and you can't actually get the hydrogen down to where the microbes are. So there is a sort of, there are schemes that can describe that in more detail, but I suppose at the moment, the model actually produces the seasonal cycle quite well. So we think with relatively simple description of the soil sink, we can get the main features of the hydrogen budget in the atmosphere right. So we don't think there's anything seriously wrong, but yes, we are quite interested in doing that better, so that there might be some dependencies on that. For example, with climate change, that soil sink might change quite a lot if you dry out the soils or you change the temperatures and so on. So, but there's a lot of interesting work about the microbes. I meant to have a picture of some microbes actually, because I think it is quite interesting. That's another topic that I know nothing about, but actually how they do it, and interestingly whether they're in competition, because those microbes can probably eat methane as well. And there's an interesting question as to whether if you change the atmospheric concentration of hydrogen, do you actually do they eat that preferentially, and then do they stop eating methane? And that might be another mechanism where you actually perturb how much methane there is in the atmosphere. So we're kind of interested in that as another possible mechanism that hydrogen can influence methane as well.
Do you have any questions? Sure. Sonia, would you like to ask your question directly through the microphone, or would you like us to read it out? So Sonia's question, Katrina, is on the curtailment slide, was the 1.1 billion figure how much the UK have had in terms of energy's worth but missed out?
Yes. So it's the total UK since we've had renewable energy under the contract for difference mechanism of payment, which we did need. We needed it to bring the cost of renewables down, which it's done brilliantly. Now we need to make sure we're not wasting it. Yeah.
Thank you from John. Okay. And the question from Abby.
Abby, your question next. Again, you're very, very welcome to ask directly. Question off. Oh, we don't have no problem at all. So Abby's question is that you said that hydrogen is well mixed in the atmosphere. If it is used in a confined space, such as a house, will enough escape from high ceiling vents to make it totally safe? Or is it well mixed? Is there a risk of explosion?
Right. So, so I don't know very much about this, but I would assume that, well, okay, if you're using it in a gas boiler, I guess you do need to be careful that you're not leaking it and creating a high level of hydrogen in your home and possibly leading to explosions. I don't know anything about this, but presumably you need, I mean, I would guess like we occasionally have methane explosions in domestic sites because of you know, bad boilers that have gone wrong. So I guess that is always going to be a risk. I guess the answer is you need well ventilated rooms and you need to make sure that there aren't any leaks from your system. But I don't really know much about that. I think the levels in the atmosphere are much lower than anywhere near where it's likely to explode. So it's only really if you're in a confined space and get high concentrations.
Thank you.
So there's a project in Spadeadam down in the Borders Cumbria area, and they've built High House, it's called. So they've built a street of houses, and they have tried to blow them up, basically, to test the safety of using hydrogen in houses and boilers, and they couldn't, and it was found to be as safe, if not safer, than methane. So they did their best to to do that. And now, of course, we have the in Fife, we have the H100 project. So just over by Methilton, they're going to be, volunteers are signing up to have hydrogen boilers and hydrogen cookers and hydrogen heaters in their homes. And there'll be a dedicated hydrogen pipeline to the homes. They get paid a little bit of money and they get new facilities, and they'll be testing that. So that's going to be happening in the next year or so. Again, it's all about public perception, confidence in using hydrogen as a fuel, and we mustn't forget that natural gas is an explosive fuel. So yeah, thank you. Thanks
Thank
for
you.
the question.
Any other questions in the physical floor? There are two more. How are we doing for time? We'll take one more. So the question from Max Coleman. Thank you, Max. Max asks, had there been experiments with different amounts of hydrogen perturbation in models, i.e. more or less than 10% addition on present day? To what extent do you expect the effect on methane or ozone to be linear with the extra H2 emission?
Yes, no, good question. And we have tested this, not me personally, but I think other groups have looked at this, and actually the response is very linear. So although we've done a 10% experiment here, I think people have done much bigger experiments and got essentially the same results, and also done a range of different size perturbations and sort of confirmed that we're in a pretty linear response. So we are fairly convinced that doing relatively crude experiments can be scaled up to any level of hydrogen that we're likely to see in the atmosphere in the next 50 to 100 years. So I think the results of the models are fairly robust in that sense. Yes.
Excellent. Thank you both again for a fascinating talk. I found it really interesting. And everyone for the questions. All that's left for me at this stage is to, again, thank our speakers and to just highlight next month's talk. It is on the 22nd of March, and our March meeting is our last meeting of the current season, and it's our student speakers. So it's really interesting to get that view. We've got two speakers again next month, and we've got Miss Phoebe Noble from the University of Bath, looking at ray tracing satellite observations of gravity waves. And we also have Miss Alice Lake from the Met Office, looking at the future of surface transport forecasting at the Met Office. So hopefully see some of you then, both online and in person. And until then, thank you all for attending. Wish you good night.